Hello, everyone. Greetings of the day. The authors and invited guests, welcome to the technical session 5A. Myself, Prashi, and this session will be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastics, it is my great pleasure to welcome you to the 10th World Conference on Information Communication Systems, Software, Security and Sustainability, WorldS4 2026, London, UK. The 10th edition of this conference is being organized in a hybrid mode. The physical event was held yesterday in London, UK, and the virtual event is being organized through Zoom from 29th to 30th of July 2026. I hope you will enjoy the knowledgeable and interactive session through the day. In this session, we have 6 presentations. Each presenter will be given 12 minutes for their presentations and 3 minutes for the question and answers. On the 10th minute, I will be raising a gentle reminder. I repeat, on the 10th minute, I will be raising a gentle reminder. There is another request to all our participants that you all stay connected with us till the closing remarks. If you have any queries or any updates, then you can write it to me in the chat box given down below. Just before we start our session, I would like to introduce you all to the chair of our session, Dr. Monica Rathor. Dr. Monica Rathor is an associate professor at Manipal University, Jaipur, with over 17 years of teaching experience in MCA programs. Also, she serves as a research supervisor at Rajasthan Technical University, Kota. She has authored more than 21 research papers published in reputed journals. We welcome you to the session, ma'am. We welcome you to the session, ma'am. Do we have
Yeah,
any opening remarks from your end?
yeah. Thank you so much for the invitation, and I'm looking forward for the enriching research papers. All the best to all the participants.
Thank you so much for your kind words, ma'am. Uh, as with permission from ma'am, now I would like to call upon our first presenter for this session. Our first presenter for this session is Manar Elod, presenting a paper on the title Automated Selection of Liver Stiffness Measurement Regions Using Magnetic Resonance Astrography Images. I request you to kindly take over with your presentation, please. Ma'am Mano?
Hello, good morning.
Yes.
I begin my presentation.
Yes, please. You can share it now.
Okay. You can see it?
Yes, ma'am, we can see your presentation.
Okay. Good morning, everyone. My name is Manar Elwed, and it's a great pleasure for me to participate in the 10th World Conference. Today, I will present our work entitled Automated Selection of Liver Stiffness Measurement Regions using Magnetic Resonance Elastography images. This study focuses on developing an automated approach for identifying clinically valid liver regions with the aim of improving the accuracy, reproducibility, and efficiency of liver stiffness measurements. This work was carried out under the supervision of Professor Salem Labidi and conducted within a collaboration between our Research Laboratory of Biophysics and Medical Technologies and the Military Hospital of Tunis. To clearly explain our work, I will briefly introduce the clinical context, describe the proposed methodology, present the main experimental results, and conclude with the contribution and future perspectives of this work. So let's begin with the clinical background and motivation of this study. Chronic liver disease may result from several conditions such as viral hepatitis and hepatic steatosis. When these conditions persist, they can lead to the accumulation of fibrotic tissue, Liver fibrosis is commonly classified from F0 to F4. The intermediate stages from F1 to F3 represent reversible stages. F4, the cirrhosis stage, is irreversible and may cause severe complication and increase the risk of developing hepatocellular carcinoma. Therefore, early detection and accurate staging of liver fibrosis are essential for patient management. This highlights the importance of reliable and non-invasive liver stiffness measurement. The increase of liver stiffness is closely related to the severity of fibrosis. MRE provides a valuable tool for detecting and staging fibrosis without relying on an invasive liver biopsy. During this examination, an external driver generates low-frequency mechanical vibration that propagate through the liver. These waves are then captured by MRI and processed to produce quantitative stiffness maps known as elastograms, where stiffer areas appear in red. During a clinical MRE examination, several complementary images are acquired. First, the magnitude images, then wave propagation and wave attenuation images, and finally the elastograms. Magnitude images provide anatomical information. Wave propagation and wave attenuation images shows how the mechanical waves travel through the liver tissue, and the elastogram represent the spatial distribution of liver stiffness expressed in kilopascals. Therefore, accurate liver stiffness quantification requires the combined interpretation of these different images. This makes the selection of a valid measurement region a complex and important step. First, the radiologist manually defines the valid measurement region using the magnitude images, ensuring that the region covers as much as possible from the liver parenchyma, while excluding large vessels, gallbladder, and biliary ducts. Then, the selected region is adjusted using the wave propagation and wave attenuation images to retain only areas with reliable wave propagation. Next, the final region is superposed on the elastograms to obtain the mean liver stiffness. As you can see, the current methods may lead to inaccurate ROI placement or the exclusion of clinically relevant regions. Also, differences in ROI placement can produce variability in the measured liver stiffness values and limit measurement reproducibility between operators. In addition, this procedure is time-consuming, particularly because several MRE slices must be analyzed for each patient. Consequently, its efficiency remained limited, especially in routine clinical practice. Overall, these limitations demonstrate the need for a more accurate, reproducible, and automated approach for liver stiffness quantification. It's in this context that our project becomes relevant, where our objective is to develop an automated methods for accurate liver stiffness quantifications using MRE, taking into account the precise selection of liver parenchyma while excluding non-parenchymal structures and areas with inadequate wave propagation. So let's move on now to the description of the proposed methodology. To realize this objective, the workflow of the proposed method is organized into three main steps. First, we perform a data collection. Second, the images underwent a pre-processing step to standardize their format. Finally, the proposed deep learning framework automatically identifies the clinically valid liver regions and calculates the corresponding stiffness measurement. Data collection was carried out from January 2023 until 2025, where a cohort of 18 healthy subjects was collected from the military staff working at the hospital, then 18 patients with different chronic liver disease like hepatitis B and steatosis were required from the gastroenterology department of the same hospital. All MRE examinations were performed on a clinical MRI scanner from General Electric, additionally an MRE device from the American company Resoundant. Of the entire cohort, 6 subjects were excluded due to severe imaging artifacts or inadequate wave propagation. So, the final study sample comports 154 subjects. For each subject, we acquired 3 to 5 elastography slices. To begin the developing of our automatic methods, we first need to select the input images. So we choose magnetic images, wave attenuation images, and elastogram images according to the objectives I outlined at the beginning. Then, the selected images underwent a pre-processing step which consisted of nifty conversion and normalization. The model we developed is a combined 3D unit model that uses magnitude images for the segmentation of liver and the exclusion of non-parenchymal structures, and the attenuation images are used to determine the region with good wave propagation. The two resulting regions are then combined to obtain the final valid region of measurement, which is well away from non-parenchymal structures and located in an area with good wave propagation. The model processes 3D volumes up to 5 slices and follows a standard encoder-decoder design with skip connections. The encoder has 4 3D levels, convolution levels, batch normalization, ReLU activation, and max pooling to progressively increasing feature channels. The decoder mirrors the encoder with up convolution layers skip connection to restore spatial information. Each decoder block also comports ReLU activation, upsampling, and the final layer uses sigmoid activation that outputs the segmentation mask. Moving now to the results. The results of our model appear relevant according to specific segmentation metrics with a DSC of 0.92, which is considered excellent, achieving a sensitivity of 0.85 and a specificity of 0.99 confirm the reliability of our segmentation. Also, visual comparison with the ground truth reveals remarkable similarity in both shape and location. The automatic methods accurately extracts the ROI from MRE images across different slices. Moreover, the projected ROIs on elastograms are well positioned, ensuring precise and consistent lever stiffness measurement. To validate our methods, it was essential to first assess the normality of differences between the two measured methods, automatic and manual. Therefore, a chaperone work test and a QQ plot were used and indicated that the data followed a normal distribution, justifying the use of parametric tests. So a paired student t-test showed no significant difference between the two methods, and the box plot confirms similarity between the manual and automatic methods. And finally, the blind Altman analyses indicate that the differences were mostly near zero, confirming the strong agreement between the two methods. Comparing our results with previously published methods for automated liver stiffness measurement in MRE, the interclass correlation coefficient of 0.99 indicating high consistency compared with other approaches. Finishing with the conclusion. The main contribution of this study is the development of a fully automated end-to-end framework for liver stiffness quantification from MRE images by combining liver parenchyma segmentation, exclusion of vessels and non-parenchymal structures, and the identification of reliable wave propagation regions. This integrated approach achieves high segmentation performance and excellent agreement with expert measurement, demonstrating that the automatically selected regions are clinically reliable. Overall, the proposed methods provide an accurate, reproducible, and operator-independent solution for liver stiffness measurement, while considerably reducing the need for manual intervention. Despite these promising results, the present study has several limitations that should be considered. First, it was conducted at a single center using one MRI system and a single MRI acquisition protocol. Therefore, the generalizability of the proposed framework remains limited. Second, the test cohort included only 13 patients. And finally, the study mainly focused on technical and quantitative validation of the automated framework. Regarding future perspectives, our work will focus on the extension of different chronic liver disease and the integration of the automatic fibrosis staging based on quantitative liver stiffness measurement and clinical characteristics, longitudinal evaluation, and finally the external and multi-center validation using larger cohorts from different institutions, MRI vendors, field strengths, and acquisition protocols. And thank you for your attention.
Thank you so much for your presentation. I would like to ask anybody willing or having any questions regarding ma'am's presentation to kindly take over. Any questions on the presentation from our presenters or any guests? All right. So thank you so much for your presentation, ma'am. Now I would like to call upon our next presenter for this session.
Thank you very much.
Thank you. Our next presenter is Hector Rafael Morano Ocono, presenting a paper on the title Digging into LLMS to Interact with CAD Software Applications, API Scripts. I request you, sir, to kindly take over with the presentation.
Yes, sure. Thank you.
Sir?
Yeah, I'm trying to share my screen.
Okay.
Here it is. Can you see my screen?
Yes, sir. It is visible to us.
Okay.
Yes.
Perfect. Okay. Thank you very much. I'm Hector Morano. I work for Tecnológico de Monterrey, campus state of Mexico. The title of this presentation is Digging into LLMs to Interact with CAD Software Applications, API Scripts. So this is the agenda I will follow. First, I will give a brief introduction. Then I will mention the objectives of this work. Subsequently, I will describe the methodology that we use. And finally, I will share the conclusions and future work. So the large language models have emerged as AI assistants, enable using to perform a wide range of tasks through natural language prompts, including solving mathematical problems and generating image or videos. This study investigates the capability of an LLM to generate scripts from the Fusion 360 application programming interface, identifies the types of CAD geometry it can create, and evaluates its ability to reproduce reference images as parametric CAD models. So here we have the objectives of this work. So the first one was to explore the capabilities of an LLMs for generated Python script to be executed in a CAD software application. The second one was to identify the type of parts that can be created using scripts. And the last one was to determine if the CAD software applications can reproduce images in CAD models. So here we have the computational resources that we employed. The LLM used was ChatGPT based on GPT 5.2 in this free version. The CAD software application in which the scripts were executed was Fusion 360. The computers employed were laptops with an i7 processor at 2.5 gigahertz and 32 gigabytes of RAM. So the methodology consisted of 6 steps. and ChatGPT was used to generate the script from the prompt requested. We can see it in figure 1. Initially, ChatGPT was asked questions to provide context on Python script generation for the Fusion 360 application. Subsequently, an image of a node, as we can see in figure 2, was provided for interpretation, and the script to model the part fusion was generated. To investigate whether ChatGPT could model a part that could be easily described, it was asked to generate a script for a cinema set, and then to assess whether it could model a mechanical part, ChatGPT was asked to generate a script to a spur gear of any dimensions. We can see it in figure 5 and 6, both scripts. Subsequently, ChatGPT was asked to generate a script to create a primitive solid, a basic 3D modeling element. In this case, it was a red cylinder. The geometry should have its base in the XZ plane. So the prompt is displayed in figure 7. Finally, the image in figure 8 was provided so that the script could be generated and ChatGPT could reproduce the online in Fusion 360. When asked about generated Python script to generate geometry in Fusion 360, the LLM responded that it was familiar with the task and could be easily generated scripts. ChatGPT even showed an example of creating a cube to generate example part as shown in this figure. After asking to generate a script to create a node, ChatGPT quickly interpreted the image's difference view and generated a script to run in Fusion 360. However, it flagged an error. ChatGPT was informed of the error and it corrected to create the part shown in this figure. It can be seen that only the color green was missing. It was asked to change it, but the subsequent code began to flag errors, so the color couldn't be changed. The result of scripting that models a cinema set is shown in figure 12. It can be observed that the solid represent a single body. The seat and the armrest edges are visible, but without any rounding or assigned color. The error was pointed out and several scripts were sent, but the results show errors. To compare the solid figure 12 with the cinema set to be modeled in Fusion 360, ChatGPT was asked to generate an image of the seat, and it provided the image that we can see in figure 13. When trying to draw a red gear, the script generated by ChatGPT produced the part shown in figure 14. The errors in the part were identified, specifically the missing red color. However, subsequently code also produced errors and the correct part couldn't be obtained. The cylinder model using the script in figure 15, it appeared to correct the only missing element was the red color. The missing color was pointed out, but subsequent code didn't work and the red color wasn't obtained. After ChatGPT was asked to reproduce the outline in figure 8, it started that lacked dimension, but would attempt to create it. The generate part is shown in this figure 16. It wasn't modeled in the YZ plane, but in the XY plane. The number of points used to represent the spline was graded, and the curvature was different, but it still has the same number of geometry entities, 2 lines and 1 spline. So here we have the conclusions. To locate the menu options that ChatGPT asks users to activate, the operator must be familiar with Fusion 360. To correct errors in ChatGPT generated script, the users must be familiar with both Python and the Fusion 360 API. ChatGPT identified the part in GPG file. However, it couldn't reproduce it with all the details, though it did generate its main geometry. Currently, ChatGPT doesn't generate a script for a complex part, but it helps identify the scripting structure, saving time so the user familiar with the Fusion 360 API can later correct it and make it work. As future work, we distinguish the following tasks. It is proposed to explore creating a script to use more complex functions, such as generating a parameterized part or exporting a part to CSV file. It is also suggested to evaluate whether other LLMs, such as DeepSeek or Gemini AI, can generate better scripts and determine their scope. And finally, it is recommended to explore generated prompts to create scripts for other fields, such as fluid mechanics, mechanism design, and machine element design, just to name a few. So thank you very much for your attention. If there are questions, I'll be glad to answer them.
Thank you so much for your presentation, sir. I would like to ask anybody of our presenters, any of our guests, would you like to ask any questions on the presentation we just saw? Okay. Due to some issues with the network of our session chair, ma'am is unable to talk to us right now. So thank you so much for your presentation, sir. Thank you so much for all the information that you have been sharing with us. Now, moving ahead, I would like to call upon our next presenter. Our next presenter for this session is Negora Primova, presenting a paper on the title Digitalization of Construction Economies in Uzbekistan, Impact on Cost Efficiency and Project Performance. I request you to kindly take over with your presentation, please. Ma'am Negora, if you are available with us, I request you to kindly take over with your presentation, please. Ms. Negora. All right. I'll call upon our next presenter for this session. Our next presenter for this session is George Duke, presenting a paper on the title From Predicting Dropout Rates to Responsible Intervention, Explainable Machine Learning for Academic Success in Higher Education. I request you, sir, to kindly take over with your presentation, please.
Hello, good morning.
Morning, sir.
Good morning.
Good morning, sir.
I'm gonna share my paper.
Okay,
Wait
sir.
a minute, please.
Okay.
Okay. I'm sharing my.
Yes, sir. It is
Okay.
visible. Yes.
Yeah. Thank you. It's a present. I'm sorry, but ocultar. Okay. It's okay. Good morning. On my own behalf and on behalf on other authors, Antonio Godinho, Moreira, and Firmino Silva lectures at ISLA, is the Polytechnic Institute of Management of the Technology, and we'll be presenting the paper from prediction dropout rates, the responsible interview explaining machine learning for academic success in either education. Okay, let's get start. My present it's the presentation. Is the question. It's very important to presentation. The main aim of this article or paper is to develop and evaluate and explain a machine learning model for early identification of students at a risk and dropping out of higher education. Okay, it's very important. The theme is very important today. It can serve as a basis for institutional early warning systems and for gradual, transparent, human supervised academic, social, and psychological interventions. Okay, it's very important. Is the problem and its importance. Okay, the problem of dropout and its importance. ICA, education dropout is a persistent academic and institutional and social loss. The authors, any authors, for example, Tinto, links persistence to academic and social integration. Being a medicine, I like work, family, and economic pressure among non-traditional students. Early warning system must identify risk without replacing academic judgment. Institutional adoption requires auditable, explainable, and human-centered models. Were the objectives in this article or this paper? Design and reproducible multi-class dropout risk artifact, compare complementary machine learning, different types of the algorithmic models and adjust stacking, combining several machine learning models to obtain a more robust final prediction. Explain a global and local risk factors using SHAP, explaining the prediction of a machine learning model, and translate probably into graduate institutional interventions. And a theory background and the method. I use in my paper, we use it in paper, the design science research. Okay? It's very important to use this type of the methodology. Methodology is a different phase linked to objectives. For example, I identify the problem, define the type of the objectives. Next, I define the design to concept, the architecture, the pipeline, and others. Okay, and demo. Next is evaluation to the metrics or representation, and final to communication or evaluation communication, this type of the architecture. Where the theoretical basis, the literature, for example, the authors into academic social integration being and method no non-traditional factors, free-based learning ensembles for education tabular data. Okay, integrated artifact. The integrated artifact is the prediction, more explanation, more governance, and interpretation. Okay, where the different problem I explain, and this is the type of methodology I use in my paper. Okay, where the artifact developer is the pipeline and architecture. Is the Empire Basic predict students dropout and academic success. I use a data set. The data set is the number of the students. For example, 4,424 students and 37 elements of students in the my study, and 217 to represent the demographic and socio-economic, administrative, and academic variables. It's a more variables to a student to completely and add to explain the type of the problems and the risk to dropout of the academy. Okay, where the type of the algorithm I use in my project? Okay, is for example, in the practice, the artifact development, I use the random forest, for example, is the type of algorithm supervising. Random forest and she's both and SVM RBF and training data and the coordinate X and Y. Is the define the probability classification probably is the type of elements is the element base is the type of the data set, a logistic and the final risk probabilities, okay, and identify the registry data. I use the data set, is the type of data set the students, pre-processing, when out driven, smoothing training, model Shizuto SVM's training, matrix validation, and SHAP explain and probability, okay? And a different type of the algorithm, I use the models and explain the type of the research and the evaluation protocol and the results. Okay, I use where the elements I use in the train and test in my algorithm. Random state is the number of elements to test the elements, the data set in my in the different type of the algorithmics. For example, where the results, the different algorithm. For example, the model random forest, accuracy, precision, recall, a few icon, and I would say rock is the type of 1VS rest rock curve staking example. Okay, it's a good accuracy and demonstrate good results. Is identify and the number of the students at the risk of the dropout or missing errors. Use the matrix confusion matrix to define the stacking confusion matrix on the test set, okay, where the positive or negative is a different variable I use in my is the free variables more important in the study. Class level OC is the dropout, enrolled, graduate, strong schematic capacity, probabilities work better as a triad signal than automatic signal. Explain at shape rivals. Is the variables more important in the contribute in my study? Okay. For example, approved curricular units, approved curricular units in the second and first semester, tweetage falls in the data age at enrollment, and a different contribution, okay, to the main drivers approved in my SHAP levels or approved curricular units, tuition-free regularity and risk emerge from the interaction between academic trajectory, administrative stability, and socioeconomic condition. Okay, is more contribution. Okay, discussion from prediction to response interview. The ensemble improves performance by combining complementary learning logics. Explainability is constitutive of the artifact, not a cosmetic layer. And the prediction only gains value when converted into graduated institutional response. A table is the table represents the graduated intervention logic by risk level. Okay, is the 2040 preventive communication self-support resource with the intervention is the academic service contact log and the moderate in 4070 tutor contact pathway review and monitoring, tutor program director contextual review, and act coordinated academic, social, and psychological support when necessary. Is tutoring, social service, and counseling document decision. Okay, Limitation, future work, and conclusion. Okay, limitation is the public benchmark, ensure reproducibility, but does not prove causal impact in a real context. Lack of psychosocial indicators, sense of biology, and digital interaction traces, a complete audit for fairness, calibration, and temporal stability is still needed. And for example, in the future work, institutional pilot, probability calibration, subgroup audit, and the temporal validation with only early semester variables. And in a summary, uh, stacking best overall performance, safe, smooth, reinforce the dropout class, shape makes risk factor visible, graduated, auditable and domain reintervention, and the conclusion. Dropout prediction gains scientific and institutional value when designing as an explainable decision support artifact, articulating a performance, explaining governance, and responding interview. Okay, thank you for your attention. Any question is at your disposal. Okay.
Thank you so much for your presentation, sir. Anybody having any questions for sir? I request you to kindly please be vocal. Any questions for the presentation? All right. Thank you so much, sir, for your presentation.
Thank you.
Thank you so much for being a part. Now I would like to call upon our next presenter for this session. Our next presenter for this session is Hasna Naushad, presenting a paper on the title Growth of Glioma, or a graph theoretical approach. I request you to kindly take over with your presentation, please.
Hi, am I audible?
Yes, ma'am, you're audible.
So I'll just share my PPT.
Yes, yes, please.
Is it visible?
Yes, ma'am, it is visible to us.
Hi all, my name is Hasna Naushad, student from the Department of Mathematics, Amrita School of Engineering, Amrita Vishwavidyapeetham, India. Today, I'll be presenting my article entitled Growth of Glioma, a Graph Theoretical Approach. My article ID is 200. Let me move on to the outline of today's presentation, where I'll be discussing with the motivation for the study, followed by background, objective, data and software used, methodology employed, results inferred, conclusion, and future work. Brain tumor affects physical, mental, and emotional well-being of a human. Glioma is a primary brain tumor which arises silently and progresses aggressively. Identification at an early stage is difficult due to the subtle nature of alteration. MRI is a common imaging technique used for the detection and identification of tumor. MRI provides a detailed anatomy of brain, but identification of an emerging lesion of tumor is difficult due to the subtle nature of the alteration. Graph theory in this context facilitates the study of complex brain structure by modeling brain as a network, by identifying brain region as vertices and their corresponding relationship as edges. It effectively quantified the characteristics of brain and their respective alterations. Moving to the background, most of the existing study in the literature, especially graph-based brain analysis, focuses on advanced tumor stages where the perturbations are highly prevalent. Deep learning and machine learning tools require large annotated dataset, but initial stage tumor data is scarce. Most of the publicly available dataset possess advanced stage tumor data. This scarcity inhibits the development of research and development in this area. To tackle this issue, synthetic oncogenesis has to be made, which also face challenges like distribution of data, location of tumor, shape and size, manual seeding, outlier handling, and so on. From this background, we frame our objectives first to construct a normal brain graph from normal MRI to extract pixel data of the tumor region from the brain tumor data, which serve as a representative feature of the tumor vertex, which is introduced in the normal brain graph to synthetically construct an abnormal brain graph using the application of vertex addition, which gives the dynamic flexibility of adding and removing vertices. Next, to compare the normal and abnormal brain network by comparing the mean adjacency values. Then to add more and more vertices mimicking tumor growth to compare the normal and corresponding abnormal network. For the current study, we have used two publicly available datasets. First, normal data. CERMEP dataset was used for this purpose, which gave T1 weighted MRI data of subjects, normal subjects. Second, the abnormal or glioma dataset obtained from BRATS 2021. We utilized the softwares FreeServer, Python, and MATLAB for pre-processing, graph construction, and analysis of the brain network. Besides, this slide also explains the methodology of graph construction employed. The pre-processed MRI was initially pixelated and cropped to remove background and skull, focusing on the intracranial and anatomical structures. Absolute pixel difference was then computed for all pair of pixels. Then, Floyd-Warshall algorithm was computed to find minimum distance between each pair of pixels. Then absolute Pearson correlation was defined on the minimum distance between each pair of pixels. This defined the adjacency matrix, the brain graph. We used a pixel-based analysis which treated individual pixel as vertices and the methodology defined to establish the edges. It defined edge weight in closed intervals 0, 1, which defines the strength of physical linkage between brain region. As adjacency value 10:1, the physical linkage between the region tends to get more stronger. Now for the construction of abnormal brain network, both the normal and abnormal MRIs were taken together. Abnormal or tumor MRI from the BRATS 2021 dataset were normalized with respect to the normal MRI data in CERMEP dataset. Pixel data of the tumor region in tumor image were then extracted utilizing the segmentation mask in the BRATS dataset. These values were tabulated for all the images. Central tendencies, mean, median, and mode were then computed. Mean of these values were selected as a representative tumor vertex pixel value. This vertex then introduced into normal brain graph to construct the abnormal brain graph by the methodology explained in the previous slide. Statistical analysis was performed, which confirmed the selected representative value was found to be a good estimate of population mean with 90% confidence interval and standard errors supported the claim. Results of the comparison study between the normal and abnormal network revealed something interesting. Though the ratio of number of abnormal vertex to the number of normal vertices were negligibly small, the number of abnormal vertices ranged from 5,000 to 12,000. The single abnormal vertex exhibited a statistically significant alteration in the adjacency of network. Brain network exhibited a consistent and relevant pattern of alteration due to the emergence of abnormal vertex, which was confirmed by paired statistical t-test, though the effective size was small. In addition, the tumor vertex exhibited a strong connection with normal vertices, which is shown in the pie plot. The number of normal vertices which exhibited strong adjacency value with the tumor vertices was noticed to be more in number compared to that of the number of normal vertices exhibited low adjacency value. This suggests that the establishment of a strong physical linkage between the normal and tumor region at the emergent stage itself. More and more abnormal vertices were then introduced to mimic glioma growth to analyze the pattern of variation. The graphs were then plotted with mean adjacency value of normal brain network, tumor brain network, normal region of tumor brain network, which are depicted by the colors green, blue, and orange respectively. They were plotted with respect to the number of tumor vertex introduced. The graph clearly depicts the fact that as tumor grows or as the number of tumor vertex increase, the adjacency of network get deviated more and more from the normal adjacency value. And the tumor vertices. As the number of vertices increase, the mean adjacency value of the tumor vertex with other normal vertices increase. which shows as tumor grows, the physical linkage between the normal and abnormal region tends to get more stronger. So, for a linear growth, mean adjacency tend to grow linearly, which further confirmed the network alteration gets profound as tumor vertices increase. Concluding, the study modeled a synthetic oncogenesis by modeling brain as a network and tumor emergence and growth by the application of vertex addition. The study depicted significant alteration in the network strength due to the emergence and growth of tumor. Analysis confirmed the alteration in the network strength at an early stage and due to the growth of glioma. Although the alterations exhibited were subtle, the same can cumulatively influence overall strength of the network. The subtle nature of alteration can lead to negligence and hence to the progression to later stages. In addition, tumor region showed strong physical linkage with the normal region which progresses as tumor grows. Network gets more and more disrupted as the number of tumor vertices increase. A linearly increasing pattern of mean adjacency difference was noted in case of linear growth. Before winding up, I would like to briefly discuss the scope of future work. The methodology took two major assumptions. First, vertex getting added without making any alterations in the existing normal brain structure, and tumor growth to be linear. So further study can be extended in this direction to address these limitations to model nonlinear tumor emergence and growth. Further study can be extended to ROI-based analysis and evaluation of topological network matrices. This study utilized a small data sample, but the study serves as a baseline and further developments has to be made. These are the references. Thank you for the kind attention and time. I welcome your questions and suggestions.
Thank you so much for your presentation, ma'am. I request any of our presenters, any guests or our session chair, if they have
Yes.
any questions.
Yes, dear presenter, I have few questions.
Yeah, ma'am.
Like my first question is like, what is your specific research gap which actually address your work?
Majorly, network analysis most probably used developed tumor stages for analysis. And also, most of the data set used class of datas, class of normal data and abnormal data which belong to different individuals. So cross-line comparison between the class of two different class of individuals uh, uh, made the incorporation of normal alterations in the brain anatomy. So rather, if the same person's normal and abnormal network is available, it will be incorporating only the adjacency alterations developed by tumor. So major gap was like we have to use the same subjects, normal and abnormal.
Okay, how did you come up to that research gap? Like, did you mention any research paper which is addressing this issue?
There are many research papers which compares normal and abnormal brain, especially when it comes to tumor. There are many research papers which compare normal and abnormal brain network, but they
Did you
belong.
include that literature review in this presentation?
Ma'am, I haven't included much of this thing.
Okay, you are supposed to include that particular literature review, wherein there should be the actual papers, like 2, 3 papers from you have concluded that could be the research gap of your study. Then you should go with the objective and other things. Okay, first we need to identify the research gap, and then the objective of the research would carry forward. Now the next question is like how many images were used for the different tasks like training, validation, or testing for your
Ma'am, for
research work?
this was a baseline study. So this
Mhm.
one actually used a smaller sample, but I'm extending the work into the higher sample size.
So was it a primary data or the secondary data?
Ma'am, it is collected from a publicly available data sets. It's a
Okay,
peer-reviewed
and
data.
you are supposed to mention the details regarding the data set in the presentation also.
Ma'am, I've given
Okay.
that.
Okay. So whatever the images are there, okay,
Hmm.
everything, the data set features should be included in the presentation.
Sure, ma'am.
And like what pre-processing techniques you have applied for the MRI images?
Ma'am, I haven't included that in the slide, but I've applied all the sorts of pre-processing like skull stripping, normalization, noise reduction, everything.
Okay. Okay. That's all from my end.
Thank you, ma'am. Thank you for the suggestions, ma'am.
Thank you so much, ma'am, for your presentation. Now, I would like to call upon our next presenter for the session. Our next presenter is A. Aruna Kumari, presenting a paper on the title Patch, a wise segmentation and classification for comprehensive diabetic retinopathy using CNN. I request you to kindly take over with your presentation, please. Miss A. Aruna, if anybody from her team is along with us, I request you to kindly take over with the presentation, please. Anybody from the team or on behalf of Ms. Aruna, I request you to kindly take over with the presentation, please. All right. So as ma'am is not there, I'll just like to call upon our last presenter once again. Our last presenter, Nigora Primova, if anybody is on her behalf over here, I request you to please take over with the presentation. Any co-authors or anybody on behalf of ma'am, I request you to please take over. All right. Seems like we don't have both our presenters right now with us. We'll take them on the next session possible. With this, I would like to conclude our session. Before I conclude this, one second. So, because they are not available with us, I just like to close this session. I sincerely thank all our authors for their excellent presentations and contribution in this session. All our presenters for being a part of this international conference. I hope this session was informative enough. We, on behalf of the whole team, thank you for your support during this 10th version and all the previous 9 versions of this conference. We will be happy to have you in the 11th version in 2027. All the participants would be getting their digital certificates through email within 2 working days. The publication will be live within 7 to 8 months. Kindly cooperate with the team of WorldS4 2026. I would also like to thank our session chair. Ma'am, any closing remarks from your part?
Yeah, I would like to express my sincere gratitude to all the speakers for sharing their insight and their expertise. And thank you so much to the organizing team for sending me the invitation. Thank you so much.
Thank you so much, ma'am, for being a part of the session. Here is a small token of appreciation from the team of ICT. So, WorldS4. I hope you'll be able to see this. Here, this is a small token of appreciation for our session chair from behalf of the team WorldS4 2026 and the Global Knowledge Research Foundation and partners. As we conclude this session, I just request you all to kindly switch on to your cameras so that we can have a quick snapshot of this virtual session we just attended. Requesting all the participants and the guests to please switch on to your cameras for a quick snapshot of this virtual session we just attended. I request all of you all to please switch on to your cameras for a quick snapshot. Requesting all, if possible, to please switch on to your cameras, please. Thank you so much for being a part of this session. Okay, please just a second. And thank you all for being a part of this session. We'll meet you in the next session in 2027. Till then, take care, stay safe. Thank you so much, all of you all, for joining us. Thank you.
Thank you, everyone.
Thank you. Bye-bye.
Thank you, sir. Thank you. Thank you, madam. Thank you.
Thank you. Bye bye.